All right, so that's conservation of mass. Now we need to do conservation of momentum. All right, so this is going to be, this has a couple of steps. What I'm going to do is first go through this using the same approach that we just used, where we're going to start off with the same initial equation. We've got momentum that we're going to conserve. So we'll go and do this first where we zoom in on a pore. And we'll do this first for just the momentum of the fluid within the pore. And then we need to scale it up and do it for a porous material that has many pores. Okay? So there'll be these two steps. The first step starts off like this. So that's our basic conservation equation. And momentum is mass times velocity. So C will be mass times velocity per volume. And the mass and the volume, we can combine those two and make it density times velocity. Okay? So that's C. And then we need to have these three terms: the storage term, the divergence of the flux term, and the source term. Okay. So the first thing, let's do storage. So storage is this. So that's going to be, it's pretty easy. Just substitute it in. Okay, so we're just substituting in for C. Okay, now we've got, in this case, we've got the flux term. That's got advection and diffusion. Now in this case, so we've got advection and diffusion of momentum. Okay, so there are, in this case, we'll have both of those things. And the advection of momentum, the general way that we're writing advection is we take the quantity C that we're interested in, and we multiply it by the moving fluid, the velocity. Or a more general way of doing it would be multiplied by the volumetric flux. But remember, we're right in the pore now, so we're just dealing with all fluid. So the advective flux of momentum, it's the fluid velocity times C, and that will equal the fluid velocity times the fluid velocity times the density, right? Because C is just the fluid velocity times the density. So that's going to give us the advective flux of momentum. Now, the diffusive flux, that's a little different. So diffusive flux, and what we said for diffusion is the way that diffusion is going to work is that it's going to be a flux that's driven by, well, for diffusion we're not relying on the fluid flowing. What we have is the flux is going to be driven by a gradient in the dependent variable. So the diffusive flux is so we're going to do a gradient, and I'm going to get this, do this in a particular way. So I have C sub x and I have the gradient in the y direction. Okay? And I mean, in a general sense, it's just going to be the gradient of c. Okay? So we've got this dependent variable, we're taking a gradient, and that is giving us a flux. All right? So I can substitute in here. Okay? So the reason I wrote it as Cx is because within C you have velocity, which is it's a vector. It has a particular direction. And since we're taking a derivative, that's going in a particular direction. So we need to define the direction of the velocity and the direction of the derivative. So what we've got here is this flux of momentum is the diffusive flux of momentum is proportional to this gradient of it's the gradient of the velocity in the x direction going in the derivative is taken in the y direction and the velocity is in the x direction. So here's what we've got. So let's say we've got a fluid that's flowing in the x direction. Okay, so this is Vx, and this is y. Okay, so if we just say the density is constant, so we don't have to deal with that, the gradient of Vx with respect to y is how the velocity changes with how this velocity changes in the y direction. Okay, well, what we're seeing there is the shear within the fluid. Because if this velocity here is greater than the velocity here, then we're having shearing within the fluid. So this derivative is the shear. And it ends up being what we'll call the shear strain rate. Okay? So if we, in this term here, this is diffusion of momentum, so this has a units of the diffusion constant, which is L squared over T. So if we work through the units here, what we get is that this thing has units of stress. And I think conceptually we see that dVx dy is conceptually a shear. And in fact, what you get here is that this is the shear stress. So the diffusive flux of momentum is the stress within the fluid. Okay? Now, we'll just use this term sigma for the stress at this point. All right, so what we've got then is that the flux is equal to the advective flux of momentum, which is the velocity times the density, and that's the advective flux of momentum, and then the diffusive flux is, actually it ends up being the negative of the stress. Okay? So that's what we get for the flux. And then for the source term, the source of momentum, the way that this works is you can let's just call this capital F for the source of momentum. We'll end up using this in some cases. The thing that is the way that you get stresses within a fluid kind of generated internally are from gravity, and that is what's called a body force. So this is going to just end up being the body force that creates like a hydrostatic pressure. that's what we'll get from that term F. Okay, so we substitute this stuff in, and the way that it's going to work is this is going in there, into the divergence. Here, that's that term, and then we just said that this is going to be equal to F. So the momentum is just by substitution. Okay, so there's the conservation of momentum. All right, any questions on that one? Okay, so here's where we were. Yeah. I'm going to write this a little bit different. So I can distribute out that. Well, let me just start off with what we had on the previous page. Okay, so what we can do, this is the divergence of these two things, so we can write it like this. And then, well, I can write it like that. Okay? All right, so now what we have to do is look at the stresses within the fluid. Okay, so the stresses within the fluid, we're going to have two kinds of stresses. If we look at a block of fluid, the stresses on that, we're going to have stresses from the pressure and stresses from the shear as the molecules flow past one another. Okay, so what I'm going to do at this point, I think, is just say that the stresses in the fluid, I'm going to write it in kind of a abbreviated way. What we're going to do is say, well, there are many different kinds of fluids, and the stresses in the fluids will vary depending on how these fluids behave. Water, would be one type, but you have other things like blood or oil or maybe slurries of materials or paint, and all of those materials have different types of behaviors. So the kind of fluid that we're going to be interested in at this point is called just a Newtonian fluid, and it's described by a fairly simple rheology. And what I'm going to do, I'll be talking more about this next time, so at this point I'm just going to say that the stresses in the fluids, let me just do it like this. Talking about stresses in fluids is going to take a bit of time, so we'll do that next time when we focus more on fluids. So at this point I'm going to say the stresses in the fluids have these two components. It has a component of pressure and a component of shear. Okay? And so we can substitute that in there. And that gives us Okay, so pressure is a scalar. So when we have this nabla operator, when we do this, when that guy operates on pressure, we just have the gradient. So that's the pressure gradient. But this tau, that's shear stress. And that's, well, we've seen pressure before. Okay, shear stress is a tensor, so we have the divergence of this tensor. Okay, so this is conservation of momentum for a Newtonian fluid. Okay, and it has these various terms. This term is what's called the convective acceleration term. So this is how the momentum is changing as the fluid is. If you have fluid converging, then the velocity will pick up, and that's a convective acceleration. This is a pressure gradient. This is this divergence of the shear. That, as it turns out, what that's going to be is how the energy is dissipated within the shear from viscous dissipation. Okay, so this will be viscous losses within the fluid. This term here, this is the only time derivative that we have, and so this is like a transient acceleration. So we have we've got a change in we could have the fluid flowing straight, and we turn up the flow rate, okay? And that creates this change in the flow rate with time. And that would be expressed as that term. And then here is our source term. Okay, so there are these 5 different terms that are describing things within the fluid. This equation here is called the Navier-Stokes Equation. And this pretty much describes this is a fairly versatile equation describing flow of fluids. Okay, it could be the air in this room. It could be the water in the reflecting pool over there, or what have you. It could be also flow through porous media. For what's generally done, though, is that we look for ways to simplify this equation. And so for flow through porous media, we've got flow through these small pores, and that is going to generally limit the velocity to quite low velocities. And so we'll say that if the velocity is low, then this term here, because the velocity is squared, that's going to be essentially equal to 0, so we can ignore that. And we'll also ignore any kind of acceleration term, and so we'll ignore that term as well. And then for now, I'm going to ignore the body forces, and so we'll get rid of that. Okay, so by treating this as a porous media problem, we can simplify it down considerably, and that allows us to write it like this. Okay? So now what we've done is, this is now the simplified equation for the pores. Now what we've got to do is scale it up. And we need an equation that applies over a larger volume. And the way that that's done is to average. So that's what I'm showing here schematically. We've been working like that, where we just have a pore, a single pore, and now we need to have, this applies just like right in, this block is like right in there. We're going to go up in scale, and now we've got several pores in here, say, and we want to have just an average property. So the way to do that is to say that this works, but we're going to average over the region. And so these square, or these kind of pointy brackets, are used to indicate that we're going to take the average. All right? So this term here is the pressure gradient within the pore, and if we average it, then this just becomes the pressure gradient over this. This is what we've called the REV. So if we take the average, then this guy here is just the pressure gradient over the REV. So that's a pretty simple one. For this guy, though, this is going to be a little bit trickier. So the first thing that we want to do, remember the general way to take an average over a volume? Remember how to do that with by integrating over the volume, right? So this average, in general, we can take an average over this volume by doing this. Triple integral over the volume, and then there's dV. Okay, and whatever we put in there is going to be the average. So this thing here is a general way to write an average. If we're interested in this divergence of the shear stress, then we put it like there. Okay, so that's the average over the volume, the control volume, or the REV. Okay, so now, so everybody's okay with that? We've probably seen, I know some of you guys hopefully have seen that before, right? Yeah, okay. All right, so now we use, I'll write this again. This thing now is called Gauss's theorem. And what Gauss's theorem says is that term equals, do 1 over volume, and now I'm going to integrate over the area, and I'm going to take the normal flux okay, so that's the normal vector, and what I'm doing is if I come up here to the region that I'm interested in, this S is the surface. Okay, and this is the normal vector to the surface, and this is the quantity that we're interested in, normal to the surface. Okay, so this is like a flux coming across the surface. So in this side, it says the average value within the region, and on this side, we're integrating the flux over the surface of the region. Okay, and we're equating those two. So that allows us to get a way to handle what that is by just looking at this thing is basically going to be the shear stress on the surface. And the way that we're going to do that is recognize that, okay, we have this region that we're interested in, but within this are these pores, and the shear stress is on the walls of these pores. So this tau here is the shear stress on the wall of the pore, and we're going to take the integral over all of the internal surface area of these pores. And okay, so yes, let's see. So in doing that, I'm kind of running out of room here. So let's. Okay, and so if we do that, then if we say, well, this shear stress is just the average shear stress on the wall of the pores, if we're integrating this average thing over all the surface area of the pores, and then we divide by the area or the volume of the pores, what this ends up being is the shear stress times the area of the pores and the volume of the pores. Okay? And if we end up saying that the pores are cylindrical, then this is the area of the cylinder, which is pi dl, and the volume of the cylinder, which is pi d squared 4l. Okay? These are cylinders these are pores that look like that. Then what that ends up doing is this complicated looking integral ends up being the shear stress. See, that cancels, the L's cancel, and it's 4 over D. Okay? So what we get from this is that we started off with this. And that's become the wall shear stress, 4 over D. Okay? All right, so now there are two more steps that we need to take. One of them is, let's see, we've got this pore over here. There's our pore. We can go and take a little block out of that pore and do a force balance on that block. And we've got pressure acting on the block, and we've got shear stress acting on the block. And by doing that, what we get up, I want to get down to the bottom of this in a couple of minutes. So we go and do the force balance, and the details of how that all works are in the notes. But what you end up with from the force balance is that the pressure gradient is equal to minus 4 times tau over d. Okay, so this is from force balance. Then we can also look at the flow itself through an individual pore, and that's from, if we assume that it's a cylindrical pore, then we get that the pressure gradient is times the flux, viscosity. So this is and this is something you can look up. It's called Hagen Poiseuille Law. Okay? So we've got three things. We've got this term here that we got from averaging over the pore volume. We got this one here that's from a force balance, and this one here that's from the flow through the pore itself. Okay? So the place where we started from too was relating on the previous page we had that the pressure gradient equals that thing. All right, so what I'm going to do is write this all out, and we should get our result. So the pressure gradient equals this averaged divergence of the stress, and that equals right here, that equals tau 4d, and that from this, that equals dp dx, and from that it equals q mu, g is a geometric factor, d squared. Okay? So that's stringing all of these different steps that we have together. We good? We've got one more step. So this is what I'm after, Q. That's the volumetric flux. So I'm going to bring that over. I'm going to basically multiply this stuff here through. So I get Q, and actually there's a minus sign in here. The sign changed. So Q, and that equals minus d squared. There's the viscosity. There's a geometric factor. And there's the pressure gradient. Okay? So after all of that, we end up here. And what this says is that the flux is proportional to the pressure gradient. And the proportionality depends on the diameter of the pores squared, the geometry. Well, there's the diameter of the pores squared, and the geometry, and that's the viscosity of the fluid. Okay?
Is that last equation supposed to be the same as the typed up one? Because if so, the G is...
Yeah, it doesn't matter.
Okay.
Doesn't matter. Let me see. The way I wrote it here, G is with mu. G is just a geometric factor that accounts for the geometry of the pores. So this, all of this stuff here is, we can lump it together and we call it the hydraulic conductivity. So this thing right here, this is Darcy's law. Okay? So when Darcy did his experiments, he showed that the flux was proportional to the pressure gradient or head gradient, and there's the proportionality constant. And Darcy's law was empirical, and it stood as just an empirical law for 100 years. And it was really in the late 50s that the people started to work out how you could show that Darcy's law really was the conservation of momentum. Okay, so a lot of times what we do is we just kind of pull Darcy's law as if it's just like an empirical law or just something that we're starting with. It's I think useful to recognize though that within just a general framework of always starting with conservation principles, that you can get Darcy's law from, it's basically an expression of the conservation of momentum with varying simplifications. Now, one of the things for porous media flow, if you increase the velocity, then you can start to get some terms that aren't really fully expressed in Darcy's law. And remember when we went back, previous page, we crossed out some terms because the velocities were small. If the velocities are not all that small, then this gives you a path forward for coming up with a way to deal with that. Okay, so these are the governing equations that we'll use to solve problems for flow through porous media. And I think that's all the time we have.